Bohr didn't know why, but only certain potential energies were allowed for electrons. If you have very specific potential energies, what do we say about the energies of electrons? The energy of electrons is what? Quantized. Now, what he said is he called these energies orbits, and he pictured them as these, orbits around the nucleus. But when you now refer to them as shells, because if you imagine, it's not like going around like this, it's kind of, now we envision it like a shell, like a spherical shell, but even that isn't quite correct. We now refer to them as shells or energy levels. Of course, we talked about putting energy into an atom. Will that move the electron towards the nucleus or away from the nucleus? If we put energy into the atom, that'll move it away from the nucleus. And putting energy into the atom moves an electron away from the which state? Away from the ground state into, what do we call it when it's not in the ground state? Excited state. Okay. What happens when an electron returns to its ground state? What's that? Sorry? It releases photons. Yes. Beautiful. Returns to its ground state, it releases photons. Okay, so we are now going to watch something about emission spectrum. Okay, so are we talking about electrons bumping up, or are we talking about electrons falling down? If we have an emission spectrum. Have a chat with your neighbor. Are the electrons going up or down? Yes. Oh, from n equals, so up would be from n equals 1 to n equals 3. So going up an energy level, or going down an energy level, n equals 3 to n equals 2, whatever, as long as it's getting closer to the nucleus. So are the electrons going up or down? Down, because when it goes down, returns to its ground state, or any other lower energy level, it doesn't have to be to its ground state, it releases photons. Another word for releases is emits. And so we are looking at an emission spectrum. So what we're going to do is we're going to excite those electrons with some electricity, okay? So there's no light going in, or maybe there is light going in, I have to think about that. But let's just excite it with electricity for now, okay? And then the electrons are going to fall back down, and we're going to get an emission spectrum. And we're going to watch this little video here, and I'm hoping, it's been a while since I've watched it, that it will have some nice pictures and things in it. Okay, there we go. And you guys caught that? It has to absorb an exact amount of energy? Yes? So discrete, that word means, in this context, it means exact. Yes? Now, there's a few blanks there for you to fill in, so I'm just going to pause it here for a moment. Let me know when you're done. Do you need glasses, Tony? You can always sit closer for videos if you want. There's like 2 seats, like with nobody in them. Okay, are we done? We need another minute? Okay. Do you notice what energy level we are starting at? We're starting at n equals 2. Okay, anytime you are absorbing or emitting visible light, you'll either be transitioning up from energy level 2 if you're absorbing, or you'll be transitioning down to energy level 2 if you are emitting. Why is it 2? Just because the energy differences between n equals 2 and 3, 2 and 4, 2 and 5, 2 and 6, those energies correspond to the wavelengths of visible light between 400 and 700 nanometers. But if it's not, if the visible light does not affect like 2. No, and it's because it's hard to see from this diagram, because this distance from 1 to 2 and the distance from 2 to say 4 look pretty similar, right? And that's because this diagram is not to scale. Okay, we would have to make it like bigger than the page for it to be to scale, and it would be really awkward. Yes?
Oh, why does it still release energy when it is absorbing?
Oh no, this is not releasing energy. This is absorption. I'm sorry, I thought it was emission because I wrote it on the sheet, but it is absorption.
Oh,
this one.
So the visible light only comes out releasing energy.
Yes, visible light comes out when it releases energy. For this one, we would be shining white light. Do you guys know what white light, what wavelengths white light has? All of them. Yeah, because if you go out and you look at the sun, and like every color, if you have white light, you have every color of the rainbow. You have a full spectrum. So what's happening is you are shining white light at that atom, and it is absorbing red of that particular energy. Okay, not all reds, just that one specific red. Yes? It's going to absorb this light blue, okay, but only that one specific light blue. So out of all of the colors of the rainbow, for this particular spectrum, and I think this is hydrogen, it would absorb these 4 colors, but only those 4 colors. All the rest of the light, would go straight through, and you would be able to see it come out on the other side. So if you then threw it through a prism, white light, certain spectra, certain wavelengths get absorbed. It comes out the other end, you throw it through a prism, and what you'll see is you'll see a rainbow, but there will be little black lines in it. Those black lines represent the light that was absorbed, the wavelength of the light that was absorbed. Does that make some kind of sense? Yes? Yes. Different atoms have different wavelengths. Yeah, because they have different amounts of electrons that repel each other. You remember that guy did all that math and it gets very complicated and it is different for every atom.
So like if an atom or a hydrogen atom got lots of like that because red light, a different atom has a really different chemical.
Yes, you can have different red lights, different whatever lights. Yes? Yes. Yeah. Now, it wouldn't be one atom absorbing all 4 colors at the same time, but what you're doing is you're shooting this light, this white light, through a sample of hydrogen gas, say. So some atoms will absorb one color, some atoms will absorb another color. Because it's hydrogen, each hydrogen only has 1 electron that can go up and down. Yeah? Yeah. Now, is there stuff for you to fill in? I don't know because I don't have a book. I ran out of books. No? Okay. Yes.
So the energy level itself, then is absorbing on the photon.
Yeah, exactly. So the electron jumps up an energy level. So some of the atoms have an electron transition from 2 to 3, and that means it has absorbed this color on the right.
Yeah.
Yeah. And we have some of the electrons in different hydrogen atoms have absorbed this purple line, and so that's going to be that black line on the left.
Yeah, so what about the colors in?
The colors in between, you mean like these ones?
Yeah.
Those don't get absorbed because, let's say we wanted a red of a lower wavelength, you would have to go from n equals 2 to somewhere in between n equals 2 and n equals 3.
Yeah.
And that's not allowed. An electron cannot exist between energy levels.
So how is that like if you shine green light through something, the green light is not anywhere, what does it be so fast?
Sorry, could you rephrase that or say it again?
So if you shine a red light, right?
Yeah.
You shine an electron, and then the photon gets absorbed and jump to energy level 3.
Yeah.
But what if you shine a green light?
Oh, if you're shining a green light, like a pure green light, green LED, which only gives you like 1 wavelength,
Yeah.
this hydrogen atom does not absorb green light. So all the green light would go through, so you would just see that green come through. If you had a different atom that absorbed at that particular green color, the green light would not go through. It would be absorbed. Okay? But we're shining white light, so we have all the colors, all the different wavelengths. And that's why we see most of the wavelengths go through and get reported, okay? But we're missing a few. And those are the ones that correspond to the energies of the n equals 2 to 3, n equals 2 to 4 transitions. Yeah? Tony?
In the video say where it's like say near I don't know if it's probably not accuracy.
That's okay.
100 volts to jump from like
Yeah.
to the N3.
Yeah.
If you have less than 100, say like around 99, then it wouldn't do the jump.
It will not do the jump. If you have, let's say you needed 100 joules to jump from N2 to N3, and you had 99 joules, it will not do the jump. If you have more, Not if you have a photon with the wrong energy. No, it won't. You can't have 101 either.
So if it's 101, then it also would not.
It also will not.
Oh.
Okay? So that's why when we're shining the light, and if we want all of those transitions to take place, we need to give it all of the different wavelengths, all of the different energies of light, so it can pick and choose which ones work for it, which is, sounds like it's human, but that's not really how it works. We good for now? Yes.
So, is that like a specific element of the period of?
Yes, this one is for hydrogen.
Oh, so like, let's say if you have like a glass where nitrogen, just pure nitrogen. Yeah, something.
Yeah.
Red light, all the red light would be absorbed.
If you shine just that one specific wavelength of red light, yes, it would be absorbed.
And instead, if you shine green light,
Yeah.
it would be punched.
If you shine green light, it will not be absorbed. Yeah. Yeah. So that was an absorption spectrum. Now we're going to look at the opposite. Now we're looking at an emission spectrum. Okay, so this is how you can tell the difference between an absorption spectrum and an emission spectrum. An absorption spectrum, you have the full spectrum and only certain wavelengths are absorbed. When you have an emission spectrum, what you have done is instead of shining light at it, you have pumped those little atoms full of electricity, and the atoms and the electrons have jumped up. Now they are falling down, and when they fall down from n equals 6 or 5 or 4 or 3, and when they fall down to n equals 2, they will emit the red, light blue, dark blue, and purple colors. And that's why you only see those 4 colors, because those are the only 4 visible transitions. So if we had something falling down, if it was up at n equals 6 and it fell down to n equals 1, what kind of light would you expect we would probably get? It's a really big energy transition from n equals 6 to n equals 1. So that's going to be ultraviolet. Yeah?
Oh, so you can see it.
Pardon me?
You can see it.
So we can't see it. Yeah, exactly. It's not that those lines aren't there, but we cannot see them. Okay, I assume that, you know, fancy scientists with fancy equipment can measure them, right? There's UV detectors and things like that, but we would not be able to see them. Similarly, if you had something from n equals 6, 5, or 4, and it fell down to 3, what kind of light would you get? Infrared, because you're talking about a smaller energy, smaller distance, smaller energy transition, and so that's going to be, pardon me? You can't see that either. Yeah, exactly. Yeah.
How fast did they jump?
I don't know, to be honest. Well, they don't jump per se. They are here and then they are there, right? So essentially in an instant. Do you know what I mean?
So if you pump electricity through that, it's like go down the energy level right after.
Yeah.
Stop that physically.
Yeah,
Oh,
I think so. I think so. The whole actual practicality of how this all works you know, like the equipment and how it happens, I'm a little dodgy on that. But that's the theory of how it works. So Bohr didn't know why this was happening, but he did know that he saw these absorption spectrums and these emission spectrum, yes? And that there were discrete lines. He didn't see an absorption spectrum where everything got absorbed. And what that told him is that electrons could only exist at certain energy levels. Had he seen an emission spectrum, which was like all the colors of the rainbow, that would mean that electrons could exist at any distance from the nucleus, but they can't.
It's only certain colors. That's how we prove that it was only certain.
Yeah, and in fact, that's not necessarily how he proved it, but that was his hypothesis based on the fact that he observed that. He was like, why is this? This is weird. If they could be anywhere, then I should see a full spectrum, but I'm not seeing a full spectrum. I'm seeing just these discrete lines. Yeah? So that was his explanation, but he did not know why. He was like, okay, there are distances, but why? I don't know. Let's leave that for somebody else to figure out. Okay. So, did you guys fill in all the blanks there? You got everything? Okay. La 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 la. What do we have here? Ooh, we have a spectrum demo, continuous spectrum, and an emission spectrum. So we're going to watch this little live demo here. So an incandescent bulb, those are the old-fashioned light bulbs that I don't know how much experience you have with them. You've had compact fluorescents and LEDs, but the incandescent bulbs are what I grew up with for most of my life, and they are based on heating the little filament in the light bulb.
Isn't it just like the light bulbs that use wire?
Yeah, it's a light bulb that has a little wire in it, a little tungsten wire.
Like you use like those like physics, like when we make circuits.
Yes, the ones in the circuits are incandescent. Yes, and they have a little wire in them, and the electricity, there's enough resistance in that wire that it heats up the tungsten. Yeah? And when things get really hot, what do?
Light.
They emit light. And the hotter they get, the more white the light. Yes? And so tungsten it has a very high melting point. So you can heat it very high. So if you've got an incandescent bulb, you're actually getting all of the colors of the rainbow emitted from the light bulb. So you have a continuous spectrum, a full rainbow.
Like efficient because like so much energy is lost.
Yes, incandescent light bulbs are incredibly inefficient. So much energy is lost to heat. On the other hand, if it's winter time and you're heating your house anyway, incandescent light bulbs are fine because whatever is lost is heat you just aren't using to heat your house. So there you go. Okay, so it's basically splitting the light just like a prism splits the light. Yeah? So what colors do you see? Red,
Violet.
orange, yellow, green, blue, indigo, violet. Yes? You see the full spectrum.
Yes, sir.
Yep.
Oh.
And then there's probably what looks like another yellow line kind of over here. Yeah? So we got a yellow and a green and a blue. So that's the spectrum of, visible spectrum of Mercury. I have no idea what he's doing. Maybe it's like an oven mitt made of birch. And sometimes you'll see some of them look quite thick. I don't think that's because they're thick. I think it's just because there's a bit of curvature probably to that diffraction gradient, which makes them appear thicker or thinner. I think you could probably get better resolution on those lines under different conditions. I don't know for sure, but I think you can. So these are the neon like you use in a neon light, right? You've seen neon lights? That's exactly what it is. It's that spectrum coming off of the neon gas. Now, one of the reasons that you're getting like more lines with these multi-electron atoms is that, do you remember we talked about those s, p, d, and f orbitals, and like they've all got different shapes? Those different shapes of orbitals all have slightly different energies. So you might have an s orbital in energy level 2, and it will have a slightly lower energy than a p orbital at energy level 2. So you're going to have a more complicated spectrum than you would for just hydrogen, which doesn't really distinguish between the S's and the P's. It's just like everything in everything in energy level 1 is the same, everything in energy 2 is the same. It just doesn't care. Do you recognize those lines? And there's probably a purple one that we can't see very well because the other one was from like a book, right? So they tend to draw things in so you can see them better. Can you think why that would be? Why would some nebula or stars have hydrogen? Yes. All stars use hydrogen as their primary fuel. They're mostly made of hydrogen, which fuses to become helium. We won't. Okay. Okay, I think we're done with that one. And we have some questions there, which we're going to look at later. I wanted to, let's see. Do you guys think you would be able to do the electron energy and light Pogel? Oh, I'm going to randomize you today. What you guys are going to do right now, while I come up with random groups, is you are going to do page 21 and 17. Have you done 17 yet? I don't think so, right? page 17, and page 21. How many people in this class? There's 26, I think. Yes.
Yeah, always. Bro, yeah.
Okay, I need to redo this.
Because I know the second one, the second one, the second one. The part of oh yeah, the first one is exceeding. Oh yeah, it's always one. So the first one is second one is second one. So it looks something like this. So this oh no, without I totally know though, like I just yeah.
25 over 13.
So I sort of look up. It's like
13, 3, 16, 10. Huh? 23. You guys don't know your student, what your number you are anyway, so you won't be able to figure it out. I'll tell you in a minute. I just have to write them down. 15, 17. 15, 17. Two, 6, 9. I'm gonna have 6.
You're Chinese. Right, you got it.
It's too small.
Oh, what? Are you like in this focus and work? Oh my yeah. This is the
I'll think it's all here. Oh, wait, no.
Okay, friends, I have your groups for the POGL. So if you've already started the POGL, too bad, because you have groups now. You'll have to go back and work with your group if you've been working ahead. So if you hear your name, you're going to come and get a little card. You're going to find your people, and you're going to go and do the POGL, which is on pages... let's see, I think it's 9.1G. Yep, 9.1G, pages 22 to 27. Okay, Katie, Juno, Kara. Katie, Juno, Kara, Claire, Samantha, Audrey. Claire, Samantha. So go grab your people and find yourself a place to sit. And if you don't know your people, call me over, I can help you find them. So last time we did our name, our grade, and something that made us happy. Today we're going to do our name, our grade, and something that irritates us. Just like a pet peeve. Okay? Pet peeve. Okay, I can't see. There's my agenda there. Oh, okay. Yeah. Stephen, did you not get a group? No. I might have missed you.
Can I go with them?
You can go with Katie, Juan, and Tony because they only have 3 right now. Okay? Yeah. Okay. Hey, hon, I'm going to get you over here. There you go. Chairs like that. And I'm going to get you guys to move over a little bit this way. Okay, so we're all across from one another. That's good.
Yeah. No, I was just doing.
Yay.
It's just crazy. It's the Irish view.
Pencil crayons. And I know we're lacking in red, so I'll sharpen some red.
Not all I do, I take one for the team, I got more vowels for the team.
I don't know. You can always come back. Just come back and figure out what you need. Right?
I completely forgot.
Red, orange, yellow, green, blue.
Well, thank you. I don't hear very much talking. We should be discussing as a group your answers.
No, no. Somebody reads question and they all. Okay, so.